Good morning, everyone. Welcome to Westpak's Product Reliability. My name is Tim Eels, and I'll be moderating today's webinar entitled Product Reliability Testing, an Overview of Environmental and Mechanical Requirements. For your information, we're recording this webinar today at our office in San Jose, California, so you can listen to it later and share it with your colleagues. Before we start, let's take a moment to make sure everyone's ready and familiar with the control panel. First, you should find that control panel on the right-hand side of your screen. You can expand and minimize that by double-clicking the arrow button at the upper left-hand corner of that window. If you look towards the bottom of that control panel, you'll see the chat pane there. And this is important because this is what you're going to use to write in your questions to the webinar team. Can you see the raised hand button there? That's the tool by which you're going to ask questions. I'd like to make sure that this tool works, and if you could please click on that raised hand button, we'll get an idea to make sure it's working. Could you take a moment, please, and click on that raised hand button? Okay, I see a few replies coming in. Thank you. During the presentation today, we'll stop. We've got three different times scheduled to stop and answer questions, so please make sure you use that feature. Also, if you're not able to attend today's session, if your colleagues aren't, they'll be able to access our materials through our website. Both the slide deck and the video will be available there. Also, both Herb and Mike, our presenters today, will follow up with you individually on any questions that you asked today that we did not get a chance to answer. So a couple of quick intros. First of all, Mike Brown is one of our laboratory managers here at Westpak. Mike started his career at Westpak many years ago while he was studying for the bachelor's degree he earned in industrial technology and packaging from Cal Poly San Luis Obispo here in California. After several years of testing products as a test engineer here at Westpak, Mike was promoted to a lab manager position, and right now he is responsible for several divisions: our reliability division, solar, environmental, and mill aerospace. Also, we have a co-presenter today, Mr. Herb Schuneman, and Herb is our president and CEO here at Westpak. He brings with him over 30 years in the test industry. Herb has a bachelor's degree in packaging engineering from Michigan State and an MBA from Northern Illinois University. One thing about Herb and Mike, they both enjoy sharing with others what they know, so that's a big opportunity for you to learn from them today. Personally, I've learned a ton from each of them. I've been at Westpak for 5 years. So I'm going to pass the mic over to Mike Brown so we can get started on today's webinar. Take it away, Mike.
Thank you for the introduction, Tim. Thank you, everyone, for joining us. So a brief agenda for today's webinar. We'll start by discussing why do product reliability testing, talk about some things to consider prior to testing, like defining the product's environment and some design and other considerations. We'll spend the bulk of the hour on test technologies, covering temperature, shock, vibration, mechanical cycling, and about a dozen other test technologies, focusing on typical parameters, test standards, and common failure points and results, and then wrap it up with conclusions and testing questions. We'll have breaks for questions a couple times, so please ask them, and we'll do our best to respond to them during the webinar. So first off, why test? First off, we have a definition for reliability, which is the ability of the product to meet the design criteria. So products will see many hazards throughout their life. Different products will see different hazards, but here are some of the main ones to consider when developing your test plan. You have the indoor and outdoor environment, so thinking about things like temperature, relative humidity, UV, corrosive atmosphere. You have rough usage and handling, so for handheld products, you might have drop or impact. Operating conditions, if something has to operate in a car, there might be vibration, or on a ship there might be vibration. And then think about shipping. Everything that's produced has to be shipped somewhere and installed somewhere. What inputs will it see during that process? Also, there may be regulatory requirements that apply to your product class. some industry standards or legal or certification requirements. And then lastly, having a reliable, robust product will ensure a high level of customer satisfaction, low warranty claims, and low long-term liability for your company. Herb, would you like to add something?
Thanks, Mike. The area of shipment and installation is one that's near to my heart because that's my background. And that's exactly where reliability started. The reason is that the shipping environment for most products represents the most hazardous group of inputs that the product will receive in its entire lifetime. So don't shy away from the reliability thing just because it works in its environment. You still have to get it there. A product is no good to anyone, including you or your customer, until you actually deliver it. And unless your client is next door, delivery is going to be, for most products, the most severe portion of its entire life cycle. So make sure you consider that. Thanks, Mike. Thanks, Mike.
All right, thank you, Herb. So some things to consider prior to testing. This mainly focuses on design. A quote from Thomas Watson of IBM, good design is good business. When you are designing your product, think about referencing existing solutions. You know, if you look at a competitor's product or a comparable product in your class, there's probably reasons why they wound up at the solutions they did. Common things we see are issues with thermal expansion, materials expanding at different rates and coming apart, a lack of strain relief and internal components, material compatibility issues, so dissimilar metals, grounding issues, plastics not being rated for their application, either outdoor light or thermal things. Problems with hardware torque or thread locker, so when vibration or other mechanical inputs occur, having hardware back out and fall apart. And lastly, production process control. Specify everything. So when you're using hardware, do you have specified torque levels? Oftentimes when you see intermittent failures, the root cause is lack of production process control. Also, there may be some regulatory requirements that apply to your product that aren't necessarily directly related to reliability, but things to think about are optical considerations, if you have a laser or some other highlight source, noise considerations, how loud is your product, if nothing else for customer satisfaction, mechanical concerns like hot or cold points, cut points, pinch points, etc. Electrical considerations, are there a risk of shock, fire, obviously if there's a risk of fire with your product, and any EMC, EMI parameters. Lastly, does your product actually do what it's designed to do? Is it effective? When we talk about pass-fail criteria, this is very important. So establishing our test plan, the design of experiment. We have to characterize or define the environments the EUT or equipment under test will see. So when possible, try to define test inputs that cover all the environments that your product is likely to see. Think about combined environments. So an example would be temperature and vibration. You have vibration induced in shipment. If the product's very hot or very cold, it's going to act differently mechanically and maybe more failure prone. Remember shipping. Everything you ship, everything you build, you have to ship, and in many cases, it's the most severe mechanical environment a product will see. Next, before you test, what's your acceptance criteria? What are your must-haves and your nice-to-haves? Where possible, try and make quantitative measures of pass-fail. And then also think about cosmetic issues that a user may reject, functional issues when your product is broken, and then if your product does get severely damaged, is it still safe, or does it pose some sort of safety hazard? Generally, testing is done in 5 stages. You have a prototype or engineering study phase, doing proof of concepts, trying things out, engineering verification, design verification, performance verification, and lastly, a mass production or final verification. One mistake we see often is people write very comprehensive test plans and want to do the full thing on their prototype product. We recommend starting small. Test temperature first is relatively quick and easy and will tell you a lot, and basic mechanical things like shock or vibration, or if it's a small consumer product, drop. Lastly, think about testing to level. If you can define what your environment will be, test to a level that represents that environment, or testing to failure or margin testing. This will help you to determine if your product fails, is it safe, and it'll show you the weak points in your product so you can improve them. At this point, we'd like to pause for questions.
Thanks, Mike. We don't have any questions in yet. Keep going.
Herb, would you like to add something?
Sure would, Mike. One of the things that occurred to me was that a lot of people listening to this presentation are already into reliability, and they know a lot of this, and that's good. So one of the things we'd like to focus on, although it's not our direct focus, is okay, what are the new stuff coming up? What other things should I be considering? And the point that Mike made about combined environments certainly represents the forefront of what's coming as far as reliability is concerned. And those combined environments I define as two or more single hazard inputs combined at the same time at varying levels. So you can think about some of the examples. Mike mentioned vibration and temperature, for example. The U.S. military found out years ago that they could reproduce field failures by using this type of test that they refer to as shake and bake that could not be reproduced with other environments. Westpak has found the same thing. We do one particular test for a product as simple and mundane as ice cream, and that involves three inputs, the temperature, vibration, and altitude, all of which have a potentially disastrous effect on, yes, ice cream. So think about combined environments in a way that is creative, and most often, if you're uncertain about reproducing in the laboratory known field failures in previous products or even in the existing product. So, okay, Mike, take it away.
Yeah, Mike, on your slide 5 there, your various engineering verification tests and such, could you redefine those terms? We had a couple of questions about that. For example, sure. EVT, DVT.
Yeah, so these first off they vary a little bit by industry to industry, but these are a pretty common summary of what we see. The first thing is prototype or engineering study testing. Sometimes this is called a notebook test. You're just trying to see if some idea or new technology works in an extreme environment. You have engineering verification, so same thing, very kind of a full assembled prototype. Does it work as intended? You have your design verification, or DVT, further along in the product development process. Your PVT, or performance verification test, and this is where, at this point, are you going to make any design changes? The PVT is the last iterative step before you go to production. And an MP, or mass production, is simply just testing some products that come off the final production line. Thank you for the question. All right. So moving on, now we're going to talk about test inputs. We're going to cover about a dozen of them. As I mentioned earlier, every product has different requirements. So as we go through this, think about what would apply to your product. As an example, though, today we're going to use a generic nondescript laptop and try to apply all these test inputs that we cover today to that laptop. So first up, we have temperature, something that everything will see. First off, you have to define the temperature range that your product will see. With our laptop, for example, it might be rated for an operating temperature of 5 to 35 degrees C. Its maximum storage temperature may be minus 10 degrees C to 45 degrees C. Uh-oh. 1 second here. Well, apologize. We'll continue going and let our IT work on getting rid of this screen. The storage conditions may be minus 10 to plus 45 degrees C. And then with many products like this, the most extreme thing you may see is the shipment environment, which can be minus 30 degrees C up to plus 60 degrees C. Although, in fact, there was a study done a few years ago showing that a hot trailer going through the desert can get in excess of 72 degrees C interior temperature. Also think about storage conditions like being inside a hot car. That can also get up to that range. The other thing with temperature range is think about the heat rejection of your product. If your product produces heat, it's an enclosed space, it may get very warm. And then also temperature rise caused by sunlight. If your product is outside, you can see a temperature rise of up to 30 degrees C above the ambient air temperature. This means if it's a very warm day, 40 degrees C, and you're out in direct sunlight, your product may have a surface temperature of up to 70 degrees C. That's pretty hot. As far as test profiles go, you can do static testing. So it's go to a certain condition, usually extreme hot or extreme cold, and stay there for 24 or more hours. For our laptop, maybe these two operating conditions, 5 and 35 degrees C, would apply, and then we'd want to cyclically operate our laptop, have it turn on and off, go to full tilt and idle to try and stress all the internal components. You might do a cyclic test, so cycling between extreme conditions of hot and cold. This will expose issues with different coefficient of thermal expansion with your materials. Or lastly, a shock profile. This is usually done on very small components. You rapidly transition from one temperature extreme to another, again as a stress test. As I mentioned, some of the common issues are different thermal expansions between metals and plastics is a very common thing where the plastic will expand or contract, the metal won't so much, and you have things coming apart. Exceeding material limits, so when you go usually with plastics above or below its operating temperature, especially if there's some sort of mechanical function. You know, if your product has moving parts, there can be issues. This is a common failure mode. One kind of top tip when you do this testing at a contract lab, usually you're renting a chamber for some period of time, so fill the chamber. You know, put 2 samples in. If you have other projects you want to piggyback, get the most out of it. We have one question. Jim.
Hey, Mike, there's a pertinent question for this slide. How do you define the operating temperature, in this case, for the laptop?
So there's a couple ways you can approach this. One thing to do is think about the industry norms. So for a laptop, it might be used indoors or in a mild outdoor environment. So think about what that environment is and what those temperatures would be. You can look at comparative products. So a laptop's a very good example. There's lots of them out there, and see what the industry norms are for the environment. Herb has something to add.
Remember also that a product like a laptop is going to be operated by an individual. So to operate, or to rather define the operating temperature environment, think of an environment where an individual operator would be comfortable. For example, how many people would enjoy being outdoors or in any environment without gloves below 5 degrees C? Probably not too many. And how many of you have ever tried to operate a PC keyboard with gloves on? I've tried it. It doesn't work very well. So you can answer that question reasonably well by thinking of how an individual operator is going to be comfortable, or at what levels they're going to be comfortable as a function of any of these inputs, particularly temperature. Okay, Mike?
All right, thank you, Herb. Next up, after temperature, is humidity. So humidity is defined in the terms of relative humidity, or air's ability to hold moisture at a given temperature. A simplification of this is that air can hold exponentially increasing levels of moisture as temperature increases. If you want more information about this, there's something called a psychometric chart that shows this relationship. So the relative humidity measure is basically a ratio of how much moisture is in the air versus the air's ability to hold that moisture. So one thing we have to be concerned with is condensation. And condensation occurs when a product is below the dew point. An example of this would be a cold drink getting water forming up on it, on its coaster. One more tangible example, though, is take Florida in the morning in the summer. A typical weather condition may be 27 degrees C, which is very comfortable, and 85% relative humidity. At that condition, the dew point is only 24 degrees C. So if you're even slightly cooler than the air temperature, condensation will form on your product. Let's think about our laptop. You're in your nice air-conditioned house, have your cup of coffee, want to go outside and sit on the porch. Your laptop is likely below the dew point, and you may have a condensation problem occurring on the inside of your product. Lastly, there's no effective humidity below freezing. So, with our testing, define the environment. Usually, shipment is the most severe for an indoor operating product. So, 2 common test conditions there are tropical, which is usually 40 degrees C, 90% relative humidity, and desert, which is 60 degrees C and either 15 or 30% relative humidity. These would be good non-operating conditions for our laptop. For indoors, there's generally no need to test. but sometimes people will test a 4 corners profile, which is low temperature, high and low humidity, so maybe 5 degrees C at 15 and 85% relative humidity, and then elevated temperature, high and low humidity, maybe 35 degrees C at 15 and 85% relative humidity. Again, these conditions will vary a little bit industry to industry. One of the main hazards here is internal condensation, especially for electronics. People try to avoid this in testing, but oftentimes it happens in the field and should be tested for. There's also some common stress tests, such as damp heat testing. Basically, it's a baking test. You go to a high heat, either 65 to 85 degrees C, and usually a high relative humidity of 85 degrees C. Have the product in a chamber for up to 42 days or 1,000 hours and see if you have moisture issues, looking through seals or other things. And there's also something called humidity freeze testing, where you go from a high heat, high humidity condition and rapidly freeze down, looking at how when water condenses and freezes on a product, if it forces mechanical separation. Think about water freezing in pavement would be an example of a real-world application of this. Common issues and results, as you would expect, are corrosion or oxidation of parts, and as I mentioned before, electrical problems caused by condensation. Herb would like to add something.
Mike, you made a good point in the first part of this humidity talk about the effectiveness of measuring humidity, or relative humidity in this case, below the freezing point of water. Remember that, that what we're measuring here is humidity, moisture, and below freezing, moisture obviously becomes a solid. It's ice, as we call it. Now, modern instruments can actually measure that level below the freezing point of water, but it doesn't mean that the product can feel it. So it's important to make sure that we got our terms here correctly. It's pretty rare that we would recommend anyone doing humidity testing below freezing. It just doesn't make any sense, and just because of its definition. So even though you can measure it, doesn't mean it's an important variable. Mike?
Thank you, Herb. One last thing to add on this is when you specify a test plan, generally we don't control any humidity level below 5 degrees C. And from a test standpoint, the colder things are, the harder it is to control humidity. And final parting thought is, like the other thing, you're in a temperature humidity chamber. Generally, the chambers can run both types of conditions, so think about combining your test plan and putting as much as practical in the chamber to get the most value. The next test input is altitude. Like humidity, this is commonly done in chambers that can also control temperature. So first off, we need to define our environment. Things are usually tested to 14,000 feet, which represents a high physical shipment elevation. In the United States, for example, Highway 50 in Colorado reaches 11,500 feet. Units are usually in elevation equivalents of either feet or meters. Sometimes things are specified in millibar or torr. Aircraft cargo today is actually pressurized for the most part to approximately 8,000 feet, so are passenger aircraft. So believe it or not, aircraft shipment is not the biggest pressure hazard that most things will see. This test is only applicable for things where there's sealed volumes either in the product or its packaging, things like potted parts, Pelican cases, things where there's sealed volumes. If your product is completely porous, this may not be applicable. So for our laptop, it may not be applicable. The tests themselves are generally very short, 1 hour in duration at an extreme high pressure, usually 14,000 feet. For shipment, sometimes 35 or 40,000 feet, representing unpressurized aircraft. And then commonly a high pressure. So low pressure is what I just talked about. High pressure would be a negative elevation, so below sea level, maybe 1,000 feet. Sometimes we'll do cyclic pressure testing at temperature extremes, just trying to mechanically stress parts. Common results are expanded and imploded parts. Oftentimes people think about venting the pressure when you go up in elevation, but they don't think about letting the air go back in when you come back down. One other common issue with products like our laptop is at high elevations the air is thinner. The laptop uses air to cool itself, and therefore it has less effective cooling. So a good test to run where you have a product that generates a lot of heat or uses air to cool itself is do a full stress test at maximum operating at high temperature at a high elevation to see if the product can still effectively cool. Now we'll move on to some mechanical test inputs. The first one is free fall drop or impact. We have two different testers here on the right-hand side. The upper one goes into the floor, so it can do very low-level drops. Those kinds of laptops on will drop down. The other drop tester below does higher-level drops above 18 inches all the way up to about 6 feet. So the environment for most handheld products will be about waist height. 1 meter is a very common, somewhat arbitrary drop environment. The test parameters, you need to define the number of drops. Things are generally drops on their faces, their edges, or their corners. The faces are the most severe for the internal components of a product because all the impact energy is dissipated along one axis. The corners, however, are the most severe for cosmetic things. If you have a smartphone and you've dropped it, I know I've dropped mine, the corners are what get beat up the most. Usually when you drop something, that's where it's going to land, a corner or an edge. It's very uncommon you'll drop a consumer product and hit it directly on a face. You also need to specify the height. As I mentioned, 1 meter is very typical, but it may be different for your product. And the impact surface. Common impact surfaces we use are carpet, laminate flooring, wood, ceramic tile, concrete, or steel. The lower drop test picture here is a steel plate. Generally, harder impact surfaces are more severe. Also think about testing to level. So as I mentioned, the 1 meter drop, or testing to failure. So if you get a more severe drop from, say, 2 meters and a product breaks, how does it break? Is the breaking just cosmetic, or does it pose a safety issue, etc.? Herb will be talking about our next two slides, mechanical shock and mechanical vibration. Herb?
Thanks, Mike. Before we jump into this, I wanted to check and see if there's any questions floating around that we could address before we move on.
Thanks for asking, Herb. So far, we're good with questions, so keep her rolling.
That's cool. Mechanical shock testing is normally conducted on a shock test machine, believe it or not. And there are two interesting and important components that we're looking for in mechanical shock. One is what we refer to as a critical acceleration, and one is critical velocity change. So let me explain those two. Critical acceleration is simply multiplications of Earth's gravitational constant, and those can build up during an impact as a result of basically the change in velocity of those things. Velocity change itself is actually a measure of what can be thought of as the energy content of a shock pulse. It's not really it's strictly energy because you don't have a mass in the equation, but it can be thought of that way. It's represented by the area under the shock pulse, the acceleration versus time pulse. Let me give you an example of how those two might be separated, and I'll use common old human head as an example. There are environments where the human head is subjected to acceleration. Football is a really good example, boxing, those kind of things. During those events, people, smart people anyway, wear a helmet. And that helmet is designed to limit the acceleration below the critical level. And for the human head, it's somewhere in the neighborhood of 12 to 15 Gs, plus or minus, depending on how hard-headed you are. I'm pretty hard-headed, but I'm not going to use myself as an example there. For velocity change, however, you can actually subject the human head to hundreds of Gs without damage as long as the duration of that input is fairly short, and therefore the velocity change, or the area under the acceleration versus time pulse, is short. Those of you who have fallen off a bicycle or hit your head on the pavement, things like that, I guarantee you're going to generate more than 15 Gs. The chances are pretty good that you'll survive that unless the duration of the pulse is very long, and you got a problem. So in mechanical shock testing, we're looking for both of those characteristics. Those are, we delve into this topic very deeply when we talk about shock response spectrum analysis, or SRS, which we'll be doing in upcoming seminars. So the waveform is very important then when we actually do mechanical shock testing, both the shape of it, the wave, and its peak and its duration. So typical test procedures use what's called a half sine pulse. It's half of a sine wave. for several reasons. One, it's very common in the environment. We measure it a lot. It's very easy to generate in the laboratory as well. Elastomeric materials or a variety of different materials are used to generate that shock pulse. And the materials are simply placed between the platen where the product is mounted and its impact surface. Peak acceleration levels are vary all over the map, and again, it depends on what you're trying to do. If you're doing acceleration test, critical acceleration, the 20 to 100 G range is very common. If you're looking for velocity change measured in inches per second or meters per second, somewhere in the neighborhood of 100 to 300 is also a very common number. It's also important to test all orientations that are likely to get inputs. But because of fixturing constraints, we typically limit that to the what we call the orthogonal axes, the X, Y, and Z axes. Both directions are important because you could have different sensitivities of the product, mechanical components, in one orientation versus another, top versus bottom, for example. There's a number of very interesting and thorough test procedures or standards that can lead you to a good test protocol. We use ASTM D3332 a lot. It was developed in the 1960s in the U.S. and has gained wide popularity around the world. It's often referred to as the damage boundary test procedure. The plot in the upper right corner of your screen shows that damage boundary plot, and it's an area bounded by critical velocity change and peak acceleration. And any shock input that can be plotted inside that region will cause damage to that product in that orientation. The bottom picture shows a typical test setup where a product is fixtured. In this case, our dear old laptop is fixtured to the top of a typical shock test machine. This is referred to as a drop shock because the table itself falls and impacts the programmers to produce a shock pulse. So the common results that we're looking for are, like I said, critical velocity change, critical acceleration, and we normally continue or step the inputs up in each orientation until failure occurs. Now, failure is an important topic, and Mike touched on that briefly. Failure is normally defined as any condition of the product where you don't want the customer to see that. You don't want that to be, in this condition when the customer gets it. So that was what we refer to as failure. Might be pretty simple. In the case of a very early Apple product, I'll pick on those folks for a while. Many of you remember the Apple III, or maybe you don't. But it was a product that had a very interesting failure level. It wasn't failure at all. Nothing broke, but one board happened to come out at a very low acceleration level. And by George, the customer didn't like it.
Hi Herb, this is Greg. We have a question. This person's interested in the constraining units during damage boundary testing. Some folks say to hold the unit or the product rigidly along all surfaces. Some say it should be constrained as it is constrained in the package, but you don't always have that at the prototype level. The question is, the first fully constrained case, is that more severe or less severe on the product?
Now there's an excellent question, and the answer is yes and no. You are absolutely correct that the best possible information comes from constraining, or what we call fixturing, the product in the same configuration in which it will receive the shock pulse, either during its lifetime or during its shipment or any portion thereof. So as a practical matter, what we'll do is to do an estimate of the fragility of the product early on in the product's development cycle using relatively simple fixturing. As the product progresses in its development, in its shape, and its configuration, we want to make darn sure that the testing also reaches the same level of maturity. And typically for halfway through development cycles, you would want to have the fixturing as mature as possible so that the results are as direction prone and that the results are believable. I don't think that that fixturing causes unbelievable results, don't get me wrong, but the better that you can fixture the product, the better the data, and the better the results, the better the decision process is going to be. What we show in the picture is just a very simple example of an initial test procedure. So I hope that answers the question. Let's move on to vibration. And again, if more questions develop, shoot them in. That's what we're here for. When we do vibration testing, we want to make sure that the test inputs clearly help us define what we're looking for. Vibration itself is not a harmful input most of the time. Vibration levels, even on transportation vehicles, which are going to be pretty severe on occasion, rarely exceed a half a G RMS, and most products will have fragility levels well above that. It's only when we excite resonances within the product or the package or both that we are concerned. So vibration testing is really what I refer to as a hunt for resonance. That's the big deal. That's the killer. There's a couple ways to do that. In the dark ages when I grew up, we would use a sinusoidal resonance search. So we'd subject the product to one frequency at a time, swept through a frequency band of interest. If we're looking for transportation stuff, that would be in the neighborhood of 200 to 300 hertz, something like that. If you're looking at, if your environment's different, if you have an aircraft mounted thing, you might extend that higher frequency band to 2,000 hertz. 2,500 is not unusual. Again, in the early days, we'd use sinusoidal input because it was easy to control, it was available, and you could use a strobe light, and everyone was fascinated with a strobe light. The reality is that almost any environment that you're going to experience in the real world is going to be random. In fact, I've heard it said that sinusoidal vibration exists in one place only in the world. That's the laboratory. That's it. Doesn't happen in the real environment. So we highly recommend random vibration. It's easy to produce these days with computer-aided controllers. It's just as easy to find resonance. In fact, the resonant frequencies that you find during that process typically are better in terms of their amplitude. The resonant frequency would be the same. But when you use random vibration, typical spring mass systems, which is really what we're talking about, respond in a way that where you have constructive and destructive interferences typically on either side of the natural frequency of a component. Those will be taken into account when you excite the product with random vibration. Sinusoidal ignores that, so you might have exaggerated results using sinusoidal. Not necessarily bad, because it's easy to identify them, but certainly not as realistic as random. So that's what we recommend. Typical procedures will, again, look at all three directions, and because this is both a positive and negative input, we simply would limit the testing to the three orthogonal axes, X, Y, and Z. And anywhere between 1 and 3 hours per axis is a typical test. If you're just looking for resonance, it doesn't take very long. If you're trying to find the results of resonance, in other words, how much fatigue does this product generate, then the time duration gets to be more important. Remember that the frequency bandwidth that you use is really a function of the environment that you're trying to protect for or to design against. Transportation, again, is typically below 300 hertz. Bare product resonance, we're looking for higher frequencies. Sometimes not just related to aircraft, but sometimes related to other things as well. There's an amazing variety of inputs. For example, if you're operating near a fan and the fan's going at 1,800 RPM, okay, you might have a higher frequency there. That's only 60 hertz, but you get the idea. So it doesn't have to be transportation dependent. It could be other things as well. Typical test procedures that we see commonly in the United States, the ASTM, American Society for Testing and Materials, for those of you who hadn't heard that before. D3580 is a very commonly used procedure, very reliable. The IEC 6006826 is another one, 264, and those type. Military Standard 810, current version of that, I believe, is the G version, will also dictate some levels of vibration testing for products. So what we're really looking for, again, is the resonances of various critical components in the product. We're looking at the frequency at which those resonate, and also the amplitude. It's a very important indicator of the damping built into the product. Both of these are very important for the ongoing quality of the product, but mostly for transportation-related stuff. Consider this, that unless your customer's next door, as I mentioned before, you're going to be shipping something, and it might be shipping for half a world. A lot of products we use in the United States are made in Asia these days. Well, that's quite a ways away. A lot of shipping is going to occur, and the one thing that's guaranteed from shipping is vibration. So you'd better know that it exists, and you better know how your product responds to it. And not only the product, but the product and the package together. For the first 10 years of Westpak's existence, one of our primary things that we did was to fix vibration problems in large package systems, where you have the package resonating at the same frequency as the product, or the structural resonance of the product, which is typically in the same range that the vehicles are going to input. So don't ignore vibration. It's a killer, and it's going to exist. Okay. Again, if you have any questions, shoot them into us. So, Mike, I'm going to turn the mic over to you, and you can continue.
Thank you, Herb. A couple more thoughts on vibration briefly. With the laptop, the pictures here of the laptop closed, probably not operating. But this is a good opportunity to think about operational vibration. The laptop has a hard drive in it, at least this one does. How does it still function as intended while it's under some vibration input? If nothing else, someone might be using it while they're in a car or a train or something. Common issues we see with a product like a laptop, or maybe something a little bit bigger, is hardware back out if you don't use any sort of locking hardware or thread locking stuff. Commonly, we'll have a big box, we'll do 3 hours of vibration, we open the box, usually you can hear it while it's going, and there's a big pile of nuts and bolts on the bottom of the casing. Oftentimes, either, again, people didn't use the right hardware, or they didn't specify torque. And then the last thing, especially with larger products, is be careful with unsupported large components. So things like capacitors, heat sinks on circuit boards, especially if they aren't through-hole or surface mount. Anything large and unsupported that hits a resonance, like Herb was talking about, comes off. All right, the next test input to discuss is ultraviolet light. Just for your reference, we're just about halfway through our test inputs. UV light occurs in the field from outdoor sunlight. The UV range itself, the definition of it will vary somewhat industry to industry, but in general it's anything shorter than 400 nanometers. There's two main portions we're concerned about. This is at Earth. The atmosphere focuses all the short wavelength stuff, and that is UVA, which can be defined between 320 to 400 nanometers, and UVB, which is 280 to 320. This testing is done in chambers usually at elevated temperatures, somewhere between plus 40 to plus 80 degrees C. One of the main reasons for that are the light sources we use generate a lot of heat, so it's a good temperature to run at that. And the other things, people think UV, they think outdoor weathering. Well, you should also consider if your product might be subjected to indoor weathering. If it's an automotive product, if it's inside the car in the window filters some UV light, but not all. And then also indoors, if something's near a retail storefront or near someone's window, it will weather. I'm sure everyone's had something at home sit by the window and it fades and weathers over time. The tests themselves are typical material selection tests. So you can see in the picture here we have a whole laptop. That's sometimes done, but usually we'll use little swatches of all the materials. With the laptop like this, it may be important to actually test the inside of the laptop. The keyboard, all the little buttons and components may be made from different plastics, different printing processes. Test all of that comprehensively. It's the little, people use the right outer case material, but the little inside stuff is what gets them. Or commonly comparative testing is done. If you have different material choices or processes, test them all, see which one does the best. After testing, think about post-test mechanical testing, so things like tensile pull on plastics, or optical or other more qualitative pass-fail results. The test chambers themselves, the two common ones today are fluorescent bulb, which is what's pictured here, or full spectrum light. So fluorescent bulb just produces UV light. The full spectrum chambers, either metal halide or xenon arc, produce UV visible and near infrared. Usually those longer wavelength lights don't have as much of an aging effect, and they're much more expensive to run. As you can imagine, the common issues: fading, legibility problems, plastics becoming brittle, etc. Next up is corrosive atmosphere. By far the most common is salt fog, and where that would come from is ocean environments and things near the ocean. The test itself just simulates a general corrosive atmosphere. It's a very good comparative test in that you can test different materials or processes, but it's not a good absolute test. And what I mean by that is you can't put something in a chamber for a week and say it's a month of outdoor exposure, because the outdoor environment of salt varies so much. There are other corrosive atmospheric tests with either acidic atmospheres, ammonia from farms commonly, but those are less common. The typical tests themselves are pretty short. 48 hours of exposure is very typical. Only the surface of the unit is exposed. So on the bottom picture here, it's a little hard to see, but you can see the laptop is in there at an angle, and that's done so that when the salt mists and falls down, it doesn't actually pool on the laptop. The other things you can see on the left-hand side are collection areas for the salt. As it falls down and collects in those areas, it's measured as a part of the test input. As you can imagine, the big thing here is material selection. You have to think about uncoated steel is a big one. When you have PCBs, all of your small components, solder joints, etc., all of that can have corrosion issues. Generally, if you're using stainless steel or anodized aluminum, this isn't an issue, but it's the little things, so things like hardware, that people forget. One other thing is to keep in mind when you do this testing is in the test, only the surface can be exposed. The chamber is very still air and it falls down. In the operating environment, you might get some salt going into your unit or corrosive atmosphere going into your unit. So think about testing the internal components of the unit separately. I think we have a question.
We're good, Mike. I'd recommend keep going.
All right. Thank you. Next up is Ingress Protection. And primarily here we're focused on water spray. The test standard we're referencing, IEC 60529, talks about enclosure testing, and it's a very generic test standard. So you could test a vending machine or a cell phone or something that's rated for a submersible environment. So first up, water spray. In the test standard, there's 8 and now 9 levels of severity. The least severe is a light sprinkling of water, and that's the upper right-hand picture. It's what's called a drip box. There's a bunch of little needle-like holes on the bottom of the drop box. You put water in it, it drips down on your product. Going to more severe, you get to water spray, like imagine a shower head, and then you get a water jet. That's what we see in the middle picture. And then we go all the way to submersion and then a deep submersion. So depending on your product class, what level of water spray is it likely to see in the field, you tested that. With the laptop, a brief light sprinkle is probably a fair thing to do, but anything beyond that would be extreme. With mechanical testing, you start with large steel ball. It's about a 2-inch steel sphere. Can you get that into a live part or a mechanical hazard, something that would cut or hurt you? Going down to a finger analog, and that's what's pictured here. It's a mechanical finger probe. Then you go down to wire, and then finally dust. Now, with all these more severe test inputs, you're looking if you can hit a live part, hit a mechanical hazard, or the product itself gets contaminated with the water or the dust. The common results with water gets in. One thing you have to be careful of, like we talked about in the beginning, is condensation. When you test, you have the water and the product at about the same temperature, but even so, sometimes you can get internal condensation forming inside the product that doesn't constitute a failure. And then with mechanical, think about pinch points or shock hazards. If you can hit a live part with your finger, you probably have an issue. Usually the mechanical problems can be anticipated prior to actually doing the test. The next 2 slides go hand in hand. The first thing we're going to talk about is mechanical cycling, and then after that we'll talk about mechanical characterization. So cycling is basically life cycle testing any moving component. So on our laptop, the big hinge on the display is one thing. different buttons, the keyboard and all the other little buttons and switches, the touch screen or the trackpad, and then all the connectors, all the ports, the USB port, everything. Those will be used many, many times throughout the product's life cycle. Will they last, a million cycles? So first you have to figure out how many cycles the unit's likely to see and what level of severity that is. You have to define the force and speed of the cycle. So as you can see here, we have an air actuator over the W key. It pushes down and releases. Typically we'll do this in a half-second to 1 second cycle, and we might test this 1,000,000 times, which may take about a week. The typical force down for a keyboard will be pretty light, but again, it's going to vary by product. When you do this, you want to inspect periodically. Generally, let's say you're testing 1,000,000 cycles, you might want to test after 1,000, 10,000, 100,000, 500,000. What you don't want to do is do a whole bunch of cycles, realize you have an issue, and not know how quickly it occurred. And then also you have to determine if you want to test by hand or by machine. Machines for simple things are much faster and can be less expensive and are very repeatable. However, they may not be as representative of a person actually doing the test. And then for more complex mechanical things, think about a prescription pill bottle. That's very difficult to test by machine. But it's doable but expensive. That may be better tested by hand. Common issues and results: quicker than expected wear out. Things breaking and falling apart much faster than they were designed for. And then also, this is what I'll talk about on my next slide, is change in the actuation or insertion removal force. So the W key may still work, but the spring back may be so weak that it's not acceptable to the user. Or the USB port may still function, but the cord just falls right out. Again, not acceptable to the user. The laptop's a very good example, but also think about, you're designing a chair. You make an analog for someone sitting in it or getting back up, or a pillow, someone putting their head on it, releasing it. This can apply to just about anything. It's just life cycle testing. The last thing on life cycle testing is usually this is done at room temperature, just out of convenience, but think about doing this at elevated or cold temperatures because especially plastic products will act very differently. The next slide, and this goes hand in hand, is what we call mechanical characterization. So if you think about how the product will be used, what's unique about your product, like your laptop, you can do quantitative characterization of most of the mechanical things. So for our laptop, I have an example here. We have a load frame on the right-hand side, and I fixtured a USB cord to a jaw and pulled it out of the laptop. And the plot there, you can see, is a force deflection plot of that being pulled out. The peak force it took to remove the USB cord was about 1.75 pounds of force. This is commonly done in pounds force or newtons, occasionally done in kilograms. So if you did this at the beginning of the test, then you life cycle tested that USB port 1,000 times and characterized it again, is it still within an acceptable level? Other things about a laptop would be maybe PCI cards, the CD drive, the accessories, another commonly overlooked thing, so the AC charger, putting the cables in and out of that, bending the cables. Are they characterizable? Do you life cycle test them and then characterize them again? One other thing with mechanical characterization is testing things to failure. So an example, the laptop has a little security lock. Put a security cord in there and pull it out. Is it actually secure? What force does that cord pull out? Things like failure on a power cord. So let's say I pulled a power cord apart somehow. Is there a shock hazard? So thinking about testing the level, characterizing what the typical user will see, and then also testing the severe, seeing how things break. All right. Next topic here is mechanical impact testing. We got a few minutes left here. We'll speed this up. So our source of impacts here could be anything like a baseball, hit and run, vandalism. Commonly this is done with steel balls, generally 1 to 2 inches in diameter. Sometimes hail testing is done using ice. Most common failure points we'll see are things like touch screens, very common on outdoor products or consumer products. They're the most fragile. Like before, you can either do test to level or test to failure, so define a minimum passing requirement and an extreme passing requirement. And with your pass-fail criteria, think about cosmetic damage the user may not like, functional damage where the product actually stops working, and then safety issues if there's severe mechanical damage or any safety issues exposed. Good example would be glass. If you break most modern safety glass now, there's no significant cut hazard. If your product had glass in it or something electrically live, something very similar would apply. The last test input we'll cover today is what we call solvent testing. So this is really a materials test. There's a list of common solvents here you'd see in a household. The big killer, based upon our experience, is sunscreen. Typical, regular sunscreen really destroys plastics, and anything that's touched by human hands is likely to be exposed to that. Typical test, pretty straightforward, is to apply and remove the solvent many times. Usually we'll use cotton balls for that, or we'll soak the device in solvent for maybe 72 hours to see how it does. As a continuation of this, there's something called abrasive scuff testing. It's either Sutherland rub or Tabor testing. And basically you rub an area, usually looking at a paint or coating or a print process. Common issues, as you would expect, are paints fading or coming apart, coatings coming apart. Plastics do not like all the solvents, and neither metal damage, corrosion, or reactions. All right, some parting thoughts on testing here for you. We have pause for questions and it's just after this. Again, start by defining the requirements. What environments will your product be exposed to? Are there any applicable regulatory requirements? And establish your acceptance criteria. What's the minimum your product has to do? What are the nice-to-haves? One thing to keep thinking about is, does the product fail safely if it's exposed to some extreme environment, like it gets too hot? Do the overtemps work and does it shut down? You should check all that. Think about the design and materials choices first. As I mentioned throughout the presentation, a lot of these problems can be anticipated and resolved with good design. Start with small portions of the test plan. Don't jump into testing everything all at once. Start with things like temperature or vibration first. Test as early as you can. Expect to have findings. And then take corrective action on those findings before you invest in all your final tooling. And lastly, as Herb mentioned and I've mentioned, don't forget you have to ship it. Oftentimes that's the most severe environment. Okay, any questions to wrap up here?
Thanks, Mike. Yeah, there are several questions, but first I'm just going to tell the audience before we go to the questions, stick around after this presentation online here, and we'll get to these questions. There's about half a dozen of them. But before we get to that, I just wanted to mention that we do have another session today. It's in 3 hours, so if you'd like to sit in on that or invite other colleagues, basically we'll be given the same presentation again in 3 hours from now. You can go to our website to sign up for that. And also, you'll be receiving an email from Westpak with both our survey as well as a link to the presentation materials. That'll be the video of today's session as well as the slide deck. So thank you very much for all of you that participated with us today. Mike, a couple of questions. One about vibration testing, going back to that. Can you tell us about how vibration, how the frequency bands in terms of maybe the test as well as the resonance might change with time during a product's life, for example?
Let's see if I can handle that one. Remember that that vibration is really a study of spring mass systems. So if something is changing over time, that means either the spring force, the stiffness is changing, or the mass is changing. And so if either one of those change, then your resonant frequency will change. There aren't too many examples of that occurring. When the spring force changes, for example, we call that fatigue, and that does happen. Any mechanical system will do that. If those of you who are automobile enthusiasts know that the springs on your automobiles are nice and stiff initially, and eventually they get a little softer. They fatigue, so that will change the resonant frequency because the spring mass system has changed. In this case, the mass stays the same, but the spring has a lower spring constant. So the only time that a time function would enter into a vibration test is if there is a fatigue-related element of of the product cycle or the product design, something like that that affects the spring rate, or the mass changes. That's it. That's the only two things that can affect vibration. Okay, any other questions?
Sure, Herb, thanks. Another question about vibration was, why do we look for resonance?
Resonance is a killer. It's also a very interesting phenomenon because we're not, as human beings, readily exposed to resonance. Anytime that we are in a resonant situation, we avoid that. We move away from it. So our products might see it, but we don't. So we don't often see that. Those of us who are a little porty in the middle know that if we're driving in a car on a certain road, we can have a resonant frequency situation develop on ourselves. You know, your stomach starts bouncing away. That can happen. But it's in a larger sense, resonance is the condition where the response of the input, the response is greater than the input, and it can be very much greater. We call it the amplification level Q, and we've seen Q values in the neighborhood of 50 to 100 times, depending on the damping of the individual system. So the reason that we want to understand resonances is they're killers. They're really killers.
So Herb, how do we find resonance in the lab? How do we do that?
Well, it's relatively simple. We put the product or the component on the table of the vibration machine, fixtured in the manner that best simulates what we're trying to simulate, shipping or in use, and then we subject that product system to a relatively low-level excitation. That can be either random vibration input or sinusoidal. And while it's subjected to that, we measure the response of that critical component with a small transducer. Smaller the better, so that we don't affect the mass. And we measure that response and then look at it as a function of the input. And where that response is greater than the input, we know that that is the resonant frequency. Most spring mass systems have multiple responses. The highest response is what we call the primary resonance, or the fundamental. Most products have harmonics or subharmonics that can be either integer multiples of that number or fractions of that number. So it's a very well-defined test procedure. I'd encourage someone to look at the standard. ASTM D3580 is the one that I use the most. But it's a relatively straightforward procedure. It's not complex. Something near and dear to our hearts, that's for sure. Anything else, Tim?
Oh, that's a good answer, Herb. I'm not sure which one of you guys wants this one. It has to do with respect to vibration and shock on connectors. Can you share any experience you might have on shock and vibration testing on connectors?
Thank you. I'll take that one. In short, when you, like I talked about just at the end of the presentation, you have to look at the mechanical characterization of the connector. So what's the insertion or removal force? When you have vibration, as one would expect, you expect things to wiggle and back out. If it can, it will. With shock, think about inertia. Basically, you have the entire system dropping with the table. As the table stops and rebounds off its programmer, as the product would, as it maybe falls in the field and rebounds off the floor, you have that big change in direction, and if the connector itself has a high mass, it's going to come out. So I can't think of a good analog at the moment, but just keep in mind if something can wiggle out, it will under vibration, and if there's a high mass especially, things will come out under shock due to inertia. I think Herb has some more to add to this.
Thanks, Mike. In our experience in many years, Westpak is 28 years old now, connectors and fasteners are the big areas where failures occur. And that's because two things that are separate are joined together. In one case for an electrical path or a signal path, in the other case for a mechanical path, if you will, a mechanical connection. Those are the things to concentrate on, the connectors and the fasteners. Those are the two areas where you can do the most good in the least amount of time. Vibration is a good excitation, a good stress for those kind of things. It's not the only one. Temperature works reasonably well as well. But remember, those don't overlook your connectors and certainly don't overlook your fasteners. Those are the two areas that almost always cause problems in our experience.
Okay, those are great answers. Question on from a human element standpoint, or human factors, let's say. How do we, at Westpak, do we test for, let's say, the human condition, the forces injected on a product by humans? What standards might you know of that would enable us to do that kind of testing through a protocol?
I'll take this one. Unfortunately, there are industry standards that define the requirements a product has to meet related to handheld electronic products, related to a handheld medical device product. But as far as defining the actual forces that something may see in the field, there aren't usually off-the-shelf standards for that. Some things that we've done, though, is think about that mechanical characterization. If you can develop something where it feels like it operates correctly, you can quantify that. Another example would be, let's say you have a cell phone, a smartphone. How much force do you push down on it with? You can characterize that. Put the phone on a small balance, push down, take some nominal data. So it all depends on your product, but if you can define what your product is going to see, what a typical environment will be, usually you can find creative ways to measure it, and then based upon that, you can find ways in the laboratory to reproduce it. Herb has more thoughts on that one.
Again, from experience, when human factors are considered important in reliability testing, we found it very helpful to utilize other organizations for that. And our most famous example is the Girl Scouts. We would have several Girl Scout troops in the area who would volunteer to open and close a handheld device 15,000 times, or to cycle a stylus in and out of its holder, where you get misalignments and things like that. So and plus they're pretty good at it. They're reliable. They use the funds to do their good work, so it works out to everyone's benefit. So that's simply one of the avenues that we use when human factors reliability is considered important.
That's great. Let's switch tracks a little bit. Had a question about, do you have any comments about choosing between performance limit testing or testing to failure?
Well, if possible, I would do both. Usually early on, your number of test samples is small. You don't have a lot of samples to test. So when you do testing, the most of the time and the effort and money is in the setup. So if you can test to level first, let's take temperature, very easy. Test to 0C and 50C. Those are your operating limits. Do that first. Then you're all still in a chamber, then go to minus 20 or 30 degrees C, go up to 80C, and see what happens. Same with all the mechanical shock, mechanical vibration. If you have some level you need to meet, do that first, then test to failure. One of the benefits of testing to failure is whatever it is, you'll find the weak parts or components in your product, and you can address those. Herb?
I'm a big fan of margin testing because it gives you a lot of information. And for most of these test inputs, margin testing, as Mike mentioned, is simply a continuation, normally not very far beyond the design limits. But it gives you the margin, it gives you the headspace so that you know not only you meet the spec, but by how much. Are you razor thin in this area, or are you fat in this particular area? In addition, if you test and you identify by margin testing which components seem to fail all the time, or which manufacturer seems to have the weakest link, a lot of these kinds of information wind up being very important later on. So if at all possible, I would highly recommend margin testing or testing the failure in these cases, because the amount of information you're going to get is valuable, and you really don't know how valuable. In our experience, it can be extremely valuable. Okay, Tim?
Thanks, Herb. Mike, here's a classic question for you from the medical device industry. How do we test for, you're talking about the fluids and contaminants, that might get on a product. How about bodily fluids? What do we use, or what can be used to test the effect of bodily fluids on materials?
That's a good question. So the most common thing you might have would be like skin oil from your hands. Sometimes people will test with mineral oil or other types of oil, trying to simulate that. Generally, the solvents that I mentioned that people put on their hands, like lotions, sunscreen, hand sanitizer, there are others, are going to be more severe than just the human skin itself. So you might test someone's hand oil a lot, but these other consumer products are going to be more severe. So generally speaking, the bare hand oil itself is not the primary concern.
Okay. Herb, you've got something to add there?
Most often, bodily fluids, kind of a strange term to many of us, can be characterized in terms of their chemical content, or at least their chemical extremes. And almost always in the testing that I'm familiar with, people will get a hold of those chemical compounds that represent the extremes of a fluid they're trying to represent, and simply use that as the exposure means for the test, either the materials or the reliability or the function.
All right, thanks. Switching tracks again, going back to the corrosion testing that we talked about. A question from the medical device industry is that does it make sense to, or would you recommend doing corrosion testing on stainless steel that might be used in a reusable product?
I would generally say that testing would not be necessary. If you are confident the stainless steel is as it is specified, and you've done nothing to it as far as welding on it or heating it where it might change its characteristics, it's generally not an issue. Another thing with this type of testing is likely that stainless steel at some point by the manufacturer has been tested to the salt fog type test, at least a typical regular one. So oftentimes you can get information from the manufacturer of the material stating they're compliant to the test. But if you drill into it, if you heat it, if you do anything to it, etc., you might want to retest it. Sure.
There's one addition to that, and that is if you use either a different manufacturer or you have two manufacturers, and normally you should for reliability, for backup, you might be able to test both of those manufacturers' products. Stainless steel is not always stainless steel. Everyone has their own little secret sauce that they put in it. So it's the real value of a test like the salt fog test is not its ultimate number. It's the comparative number. You know, which one's better, and from that standpoint, it's a relatively easy test to run. It's relatively cheap, and it'll tell you whether manufacturer A is better than B or vice versa.
All right, thanks. Here's another question. Here's a classic one, but I'm surprised to see it come in from our audience. It's great. The question is, if I have very little time or resources, what test should I do?
I'll take that one. I appreciate that. I think the test you should do first and foremost is temperature. Absolutely everything will be exposed to temperature. It's very fast and relatively inexpensive to run. I talked about in the slides you generally want to do 24-hour tests at each condition. You can do much less. The chambers can transition quickly. Test to your extremes where possible. Do humidity, so maybe a cold temperature, high temperature, low humidity, high temperature, high humidity. Have the product operating if you can. You can do all of that in a matter of a day. And then the other thing, too, is the mechanical stuff. Mechanical shock, mechanical vibration. Those tests take a matter of hours to run and will just give you a lot of data about the overall durability of your product. Where possible, do margin testing. So test to some typical level if you can define it, and then test to some extreme level. If you can do well in that extreme level, you should be pretty confident you'll be okay. Hope that helps. Herb?
One additional thought there is that that question opens up something that's very, very common, and that is in the prototype stage, the units to test are scarce as hen's teeth and as costly as true love. It's really it's amazing. So oftentimes we'll have people come in saying, holy cow, I've only got one of these and I've got all these tests to run. And as Mike pointed out, by selecting the test procedures, which you did a very good job of carefully, you can get a whole lot of information on a very few or even a single sample. To be honest, I've done characterization more often on a single product than on multiple products. So yes, you can do it. One can often ask, well, what's the result of that? You're beating this poor thing up in every which way to Sunday. So what's the result? How reliable is the data? think of it this way. A product with multiple cycles on it is likely to fail quicker, so the results tend to be more conservative. In other words, if a product is going to fail at 50 Gs and you beat it up ahead of time and it fails at 40, that gives you a more conservative number. And in some cases, that's beneficial, as long as you understand which direction it's going to go. So again, you can get a lot of data on a few number of samples, but it's very imperative that you select your test procedures in the right sequence and in the right magnitude in order to optimize your data input. And Mike did a very good job of giving you a general outline for that, but we can help individuals do that as well. Okay, back to you, Tim.
Herb, that's a great answer. While you're on the topic of prototypes, there's a number of people in our audience that are involved in new product introduction. So here's a question I'd like both of you to address, but Herb, you can start it out. With respect to testing prototypes, what are that have never been tested before? For example, maybe a client brings in 1 or 2 samples of a prototype product that's never been tested. What are the types of failure modes you typically see on products like that?
Well, in general, the failure modes are as varied as the products themselves. What we try to look for are again, conditions that are outside the bounds that you want the client to see in terms of the product functionality, aesthetics, or a variety of other things. So it's a kind of a personal component type of thing where you can't generalize on the failure modes. But we certainly look at changes. For example, if we're doing a vibration test and we reach a resonant frequency and then the darn thing changes, and we say, let's see, the only thing that can affect that is mass or spring rate, and mass doesn't change, so the spring rate's changing, so this thing is fatiguing, or a fastener is coming out, something like that. So there's a number of key things that we look for. Changes in the response of a product, changes in its color, changes in its temperature, any of those kind of things are clues or red flags that something's changing. We've been able to cause something to happen, but exactly what that is varies from product to product. You get better and better at it as you do more and more of this testing, I have to admit, but there's no one or two or set of things that you'd be looking for. It's very, very product characteristic. It's not very generic at all.
I think it's a great answer. I tried to jot it down here about 5 or 6 things that you might think about starting with. One of the first things, and we covered most of this in the presentation, is with a prototype product, what were the production specs? As far as, all the process might have been done by hand, so if there's soldering, adhesive applied, torques, that sort of thing, oftentimes those aren't specified or aren't recorded. And then also the bill of materials. If you have a prototype product, you might be using some off-the-shelf RTV you got from Home Depot that may not be the final material, and those can commonly cause issues. Exceeding material limits, usually thermal, but sometimes you're outside of the application. A good example would be using a plastic that's not rated for any UV exposure. You get to a little bit of outdoor UV exposure, you have a big problem. Different coefficient of thermal expansion, things coming apart as they heat or cool. Dissimilar metals is a big issue, hardware especially, where you have corrosion between aluminum and steel or other materials like that. And then the last thing, too, is the failure okay? Is it a cosmetic issue? Is it a functional issue, etc.? With all of these, if you can, have the design engineer or the people that built it come to the test lab and witness part of the testing, or when you get the product back and you get the test report, go over it so they can learn from all these findings. Just to pass-fail, it passed, it still runs. Okay, that's good, but there's usually a lot you can see after these environmental exposure tests in your product that you can learn from.
Mike, on the topic of the, you mentioned the test report. For a new product, such as a prototype product, what type, can you describe the types of information that the test report would contain that would help the engineer who's receiving that report?
Absolutely. It's going to vary by from test lab to test lab. One very important thing, though, is to specify what you want out of the testing. What is the purpose of the test? So at a minimum, the test report will have some basic description of the product, what was done, a thorough description of the test that was done. So let's say temperature will list of conditions we ran, how long we ran them for, picture of the chamber and setup, then also the resulting data from that, temperature, humidity over time. So whatever the test input is, all that information will be there. As far as the product itself, as a contract test lab, we'll report on what we observe. If you specify some sort of operational functional check, hit these 5 buttons in sequence, tell us what the output data is, we will report on that. Generally with products, though, we, if possible, encourage our clients to be in the lab to run the functional testing themselves or to witness the functional testing, because they can better record the operating parameters of their product than we can. So to wrap that up, specify what you want, but at a minimum, you should have all the data in the report about what the tests were and any kind of gross visual observations. Herb would like to add to that.
Thanks, Mike. In addition, I'd like to point out that we at Westpak consider our report to be the product that our clients pay for. And so we take a great deal of care in putting ourselves in your shoes and to describe the test inputs and everything that Mike mentioned in a way that if you pick the report up in 6 months or a year, you'd be able to say, oh yes, that's exactly what we did, and yes, we got those results. So the report winds up being a pretty key document to the whole thing. It's the results. That's really what the client pays for. And so we try our best to make that report as descriptive as possible, both in the verbiage and the photographs and other things that are used to describe fully the inputs and the results and what those results mean. But again, for reliability testing, there's no one better than the product designer or someone from the company to really get in and nitpick the product after it's gone through all these hazards, all these torture tests, if you will. So both of those are very important.
Herb, question on new products. Let's say we've got a new client that's never done business with Westpak before, and they wanted to request that a test be done at Westpak. How long would it take to get from the point of submitting a request to getting a test report back, that full cycle? Can you describe that?
Varies from a day to a year in our experience, and it all depends on the nature of the test, things like that. What we encourage people to do is to, if possible, come to the laboratory and see the inputs and talk to us, or invite us to your facility where we can do something similar and come to an agreement about what you want done and how it should be done, things like that. From that data, what we've established a procedure to be is we'll then present a proposal to the client saying, we understand you want to do this over this period of time at these particular levels in this particular sequence, and then we'll identify those sequences, the procedures, the protocols, all that kind of stuff, the time necessary for doing it, the number of samples, and the ultimate cost that would, as best we can predict it at the time. Because of the variability in this, it's not always exactly that number. Sometimes it's less, sometimes more. But the point is that we'll create what we call it a proposal or a contract that will describe exactly what we think the client is asking us to do. And once that's done, that's kind of our handshake that says, yep, that's what we want done, and then we say, yep, that's what we're going to do. And then we go ahead and do it. That process typically is going to take in the neighborhood of 2 to 4 weeks, depending on, again, on the product and the inputs and the extensive nature of it. But again, that can be much shorter or much longer. Again, it depends on the test procedure. But that's what I'd recommend, and that's fairly common, not just with Westpak, but with almost any testing laboratory.
Thanks, Herb. We're going to do one more question, then we're going to sign off today. Mike, the question is, what types of equipment does Westpak test?
We test just about everything. One of the fun parts about working here is trying to describe what we do. So we do anything from a cell phone to a server rack, a toaster oven to a television, just about anything. So a lot of small consumer electronic products. We test a lot of medical device products, both handheld products and capital equipment, large wheel-around carts and scanning things. We test a lot of capital high-tech equipment, so things like server racks or other kind of advanced computing things. We test various kind of robotic and vehicle type products. all sorts of stuff. If you have a specific question or product, please contact us or email us, and we'll be happy to follow up with you. Herb has a big smile on his face and wants to add something.
It's funny because we started our life doing primarily packaging or shipment-related testing. So the answer to the question of what kind of products that you test is similar to saying what kind of things are on a truck, and the answer is darn near anything. So consumer products. Last week we were testing a bunch of food products, liquid food products, and pallet loads of the darn things, along with a server rack from a very well-known electronic company, and anything in between. So if it's on a truck getting vibrated, chances are pretty good we either can or have tested it.
All right. Well, this brings us to a good wrap-up point. We'll just brief 1-minute information about Westpak. We were, as Herb mentioned, a 28-year-old company. We were founded in 1986. We do just about everything that we've discussed today as far as test inputs. We have a laboratory accreditation to ISO 17025 from A2LA. In addition to what we've talked about today, we do a lot of package testing, anything from small single parcels up to crates and pallets, less than truckload freight. We also can do dangerous goods packaging certification if you're shipping something flammable or biohazard, etc. We do a lot of materials testing on plastics and paper materials, a little bit of metals. We do cold chain testing on cold pharmaceutical or food products, and a whole bunch of other related things. As you can imagine, with the test equipment we showed today, there's a lot of different uses for that test equipment for different industries and applications. And one last thing I wanted to mention is our door is open. When we run testing, you're welcome to be here and witness it. You'll learn a lot more about your product when you do so. We're here to help. So if you have any questions, any needs, give us a call. We're here to help. And Tim, I'll have you wrap up for us. Thank you, everyone, for attending.
Thanks, Mike and Herb. You guys did a great job today. I just wanted to mention again to our audience that we've got a second session in about an hour and a half, so please refer your colleagues. You can sign up for that if they haven't already done so from our website. Expect our email in the next couple of days with our survey as well as links to our slide deck and the video. My name is Tim Eels. I've been today's monitor. Thank you very much for joining us. We've really enjoyed talking with you today and sharing all the fun that we have here at Westpak. Take care.